Well, it's official, folks. Looks like we can get started finally on our first day back after the long break. Welcome back, everyone. Any questions that folks would like to start off with right away? Okay, well, for the announcements, I guess we should talk about the projector. I think they fixed it. It hasn't been having any of the weird strobing effects that folks might have saw if you came into the class. Sorry for the abrupt cancellation. They decided to upgrade our projector over the Thanksgiving holiday, which sounds like a great idea, but they never actually checked if it was working, it turns out. So a team of people came into the classroom and did get it working for us finally. It's a nice projector. The screen resolution is a lot bigger, so we'll be able to do things like side-by-side calculator with a document much easier. It also means stuff could look a little bit distorted. So let me know at any point if things aren't just zoomed in enough, things like that, since I'm kind of just relearning how things look and work based off this new resolution. Aside from that, where we're at so far is section 12.1, and we should be done with this one after about a day and a half or thereabouts. Then we'll take a look at a confidence interval procedure. We want to spend enough time to do at least a few good examples on this thing. And so after that's completed, if there's enough time left in the week, we'll go to section 12.3 for hypothesis testing. If that one doesn't get complete out in its entirety, that's okay. We'll still put it on the final exam, potentially as an extra credit question. And we'll also make sure that when we get to the next week, I should probably be looking over here. When we get to this next week, I want to ensure that we have at least Wednesday and Thursday for reviewing for the final exam. So if we have to cut section 12.3 a little bit shorter to make that happen, we'll definitely make that happen. So that's where we're at so far, folks. Any questions or comments so far? Okay, well, with what we're going to be doing is pretty much we're redoing the central limit theorem. When we were back in chapter 9, section 9.3, the sampling distribution of the statistic p hat, we were told it's approximately normal. We had the mean being p and the standard deviation being this quantity. We had to change it to a standard error to do a confidence interval. And then we use these ideas for the hypothesis test. So essentially, we're just redoing all that kind of work there and looking at the sample distribution if it's a sample mean. So x bar instead of p hat. That's really our only change. Any questions about that so far? Okay, and just to make sure this doesn't disappear forever, let's actually put it in our notes. In section 12.1, I'll put it right here as our set of announcements. So we did start 12.1, but we really didn't do too much. I think we spent about the last 5 or 7-ish minutes last Thursday before going to the break discussing what we're going to be doing in 12.1. So the first thing we discussed is just a reminder of some of the vocabulary and terminology that we've seen. So the population characteristic will always describe the population, and it gives us parameters like mu and sigma and so on. A statistic will always describe the sample, and it gives us the statistics like x bar and s. One thing we can put on the paper so far is just a reminder that typically in a statistical problem, the values of mu and sigma are unknown. They can be calculated exactly, but in order to do that, we would have to gather a census, which involves every single member of the population. Sometimes that's just feasibly impossible. There might not be enough time, there might not be enough money, manpower, things like that to actually conduct a census, depending on what the population is. And so instead, we calculate the statistics. And here's what the statistics do for us. Even though mu and sigma are unknown quantities, we can say that mu is well approximated by the sample mean x bar. The statistic is a known value. We grab the data and we crank it out. We'll throw information to the calculator and find its exact value. And we can also say that sigma, it's a second population characteristic that we have to deal with if we're dealing with numerical data. This one is well approximated by S, the sample standard deviation. We want to do better than just the approximation. So right here, we're going to try to give a confidence interval procedure, and that will be section 12.2. But before we can do a confidence interval for mu, the population's mean, we need a brand new central limit theorem. And so that's why we're here. We're going to take a look at the sampling distribution of x bar as opposed to p hat. So that's all just tying together information. Any questions so far, folks? Okay, next thing we took a look at was this gnarly little graph right here. And our reminder is, whenever we go to gather information from a population, the population has its own distribution. It might be normally distributed, it might be skewed, could be terribly skewed. But when you calculate the statistic, call it X bar or Y bar, you're only putting down 1 point in the sampling distribution itself. So the sampling distribution of either Y bar or X bar is going to be the all possible values of that sample mean that could ever be obtained. And already it's apparent through the central limit theorem, this distribution looks like it's normally distributed. It's unimodal, it's bell-shaped, mound-shaped, as our author says. And so if we want to draw a curve, it might look about like this. So there it is. That's our sampling distribution of Y bar. That's just what they used in this textbook right here, the statistics for life sciences. Think of Y bar being completely synonymous to X bar. It'll be the sample mean either way. So the central limit theorem, now that we have this on the paper here, it says, suppose X bar is the mean of the observations in a random sample of size n of a population that will have a true mean mu and a true standard deviation sigma. Then the first rule says the mean of X bar, let's blow that up a bit. It's called the mean of X bar because of the mu sub X bar right there. It's equal to mu, which means our statistic is really trying to estimate the correct quantity. So the average value your statistic ever takes up is mu, and that means in our diagram here, here's what mu is going to be, the central value in this normal distribution. Next, the way we calculate the standard deviation of X bar, let me make that one a little bit bigger too. Is we take the old standard deviation, divide by the square root of n, and that's the sigma X bar right here. So we can say the mean of X bar is mu through the central limit theorem. The standard deviation of all the means, so sigma X bar, is going to be the true standard deviation sigma. Already that's a bit of a problem for us. Divide by the square root of n. This is problematic right here because recall, sigma is an unknown quantity. That's okay in a sense. We can estimate it using S, the information from the sample. But if we did that, we're not using sigma of X bar any longer. We're using a brand new standard error. And so that's the next component we'll need for our confidence interval. But so far, that's what the central limit theorem is telling us. The mean is just what we want to estimate. The center is right at mu. We know what the spread is, but we know we have to estimate that as well. And the final major thing is rule 3. It says when the population distribution is normal, the sampling distribution of X bar is also normal for any sample size n. So if you knew this underlying population was nicely normally distributed, this is as well, and the sample size doesn't even matter. That sounds really awesome, except you also have to remember that the normal distribution is completely made up. It's a mathematical fiction in the sense that someone came up with an equation. Let's take a look at what that equation is. There's the equation, and they use this equation to just fit a curve to something that happens in real life. That's just modeling. This is an approximation of reality. It's not exactly reality. You can't say heights are exactly normally distributed. We're just saying somehow this function with the right value of mu and sigma gives us a curve that does a decent job of modeling what's happening in real life. So going back to this document, it's saying when the population is distributed normal, that's a huge problem for us. That means rule 3 only works for mathematical problems exactly. Real life doesn't have exactly a normal distribution. So that takes us to rule 4. That one fell off the page. Let me put it back down here. Rule 4 says if your sample size is large enough, then that's okay. Your underlying distribution never had to be normally distributed. In fact, the underlying distribution could be skewed, sometimes very skewed. And that's okay if your sample size is large enough. So for a large enough sample size, the central limit theorem still works for us. And for a really not the greatest rule of thumb in the world, but definitely good for introductory class, the central limit theorem works if the sample size is at least 30. That's not a bad rule of thumb. It's the one our author is going to use, so you'll see this used in WebAssign. I feel like as far as rule of thumbs go, this one deserves a disclaimer. Let's put it in right here. The greater the skew, in the underlying population, the larger the sample size. That is needed. So it's a great rule of thumb, but it's a dangerous one as well. Let's add one more thought and mention here, there are populations for which n bigger or equal to 30, let's say here more specifically, n equals 30, will not suffice. Or even n equals 100, and so on. We can make a population or find a population in real life where the skew is so bad, you might need sample sizes to be around 500 or maybe 1,000 to overcome the apparent skew that we're detecting in the population. We've seen that kind of data before. Let me show you what it looked like. So for a problem where the central limit theorem is going to break apart if our sample size is like, say, 30 or 40, could be something like, say, this one. Let me see if I can find it here. Central variability for skew distributions. That sounds like we're getting close. That one's not too bad. That's not the one I was looking for, but it's definitely problematic. There is one other one that was even more skewed. Let me see if I can find it real quick here before we waste too much time. Sorry, I thought I knew exactly where it was. Skew distributions, box plots possibly. Oh dear, I'm not finding it. But let's settle instead for this one right here. This one's not too terrible. And I think that our author's rule of thumb of n equals 30 might not be too bad for this particular distribution. But if the skew was worse, if, for example, we had something that went like this, we had a data study from Glassdoor that had like CEO pay as a ratio to the median worker, but I'm not finding that data set. If it looked like this instead, let's say our distribution goes, so 2 values here, and then now some more data out here. And just for the fun of it, let's put something even further out here. If our data looks like this, if it's this bad, n equals 30 is too small for a sample size. For these kinds of data, we might need something around, let's say, sample size of 200 or something even larger to compensate for the amount of skew that we see here. So let's take this, and just to connect that thought, let's put it down in this document here as well. So if we have too much skew, then our rule of thumb does break down. But for the purpose of our class, we're not going to be analyzing problems like this, where the underlying population is terribly skewed. We're mostly going to look at more typical distributions. When we check conditions, we'll just look at the sample size and see if it's reasonable by this rule of thumb. I'm mentioning all of this because if you are taking more statistics, you should know that that rule of thumb is much more dangerous than the one that we did for p-hat. where number of successes and number of failures had to be larger than 10. This is a tougher rule of thumb to actually apply and stay safe most of the time. Well, that's finally the whole central limit theorem. If our distribution is not too bad and our sample size is large enough, around 30 or larger, then this picture up here is correct. For even a skewed, not normally distributed population, sampling distribution is still normal. And the larger your sample size gets, the more normal it becomes. We get more and more accuracy the higher the sample size. So that's it, folks. That's the central limit theorem. Major things we need to know is, well, if it's normally distributed, we can calculate through here to some degree. We just need to know what the values of mu, sigma over root n ought to be. In hypothesis testing, mu is specified because we're testing against it. But in confidence intervals, we don't assume a value for mu. We're just trying to full on estimate this quantity right here. So for these notes, instead of just talking about the central limit theorem, we're going to give this a try. Let's do a confidence interval right away for mu and just see how it goes with the methods we have so far. The way we're about to calculate a confidence interval is the way that they did it historically in the past, not too long ago, actually. Any questions at all, folks, before we go for our first rodeo with this new theorem? Okay, so down below, here's our new example. We've seen this data before, but now we can do a little bit more with it instead of just looking at graphs and things like that. For a reminder, let's read through it just to refresh our memory. It says, radioactive cesium, cesium-134-137, is a waste product of nuclear reactors. That looks like it's context, so let's go to a page break here. A study examined the radioactive cesium tissue concentration of a random sample of 16 Pacific bluefin tuna. So from that statement there, let's record a sample size in case we need it. N is 16. This was captured off the coast of California 4 months after the Fukushima nuclear reactor meltdown of 2011. And this is an interesting study since when they said 4 months later, and they're looking for tuna, those tuna presumably had enough time to mix around in the Pacific Ocean so that when they took their sample, it might have been representative of more than just off the coast of California. So their findings go like this. It's in units of becquerels per kilogram of dry tissue. The becquerels are a measure of radioactivity. The dry tissue is the fish being ground up as they look at the ratio of those. So we have all these data values here. They tell us next, historically, the population mean radioactive cesium tissue concentration has been below 2. That's not something we necessarily need to record, so let's use this pen. They're saying mu less than 2 becquerels per kilogram was the historical value of these fish. But then there was a meltdown, water was leaked into the Pacific Ocean that was radioactive, and now look at all these fish. They're definitely more radioactive than 2 becquerels per kilogram. We don't need statistics to determine that, but we do need statistics to now estimate the current value of mu, not the historical one. It says next, assume the population standard deviation is 2.95 becquerels per kilogram. That's a massive assumption, and this is where the procedure is going to go a little bit awry. This is why we have a next section, 12.2, where we're building a little bit more on a confidence interval. This is something that was not done historically, but something we're going to do. We're going to assume it's true that sigma is still 2.95 becquerels per kilogram. And here's the problem with that. Sigma is a population characteristic. It's the standard deviation of the entire population, just how mu is. Mu is the average, the mean value of the entire population, another population characteristics. Like we said, in a real statistical problem, mu and sigma are both typically unknown. This might be okay, but we're not biologists necessarily. We're not experts. And me, as a naive person, a lay person, when it comes to these ecosystems, I would assume if mu changed, so would sigma. If something massive happened to the population, I'd assume both would change. There might be a reason that biologists could explain why this is still reasonable, and we're just going to run with it and see what happens. The next statement they say here, the measurements follow a normal distribution. That's a huge assumption as well. This tells us immediately right here, the sampling distribution of X bar. I almost want to say p hat because we've been dealing with that statistic so often, but we're changing to numerical data. So X bar is our new statistic. The sampling distribution of X bar is also normal by, oh geez, I think it's rule 3 of the central limit theorem. Let me double check before I just leave that on the page. Rule 3 of the central limit theorem says when the population distribution is normal, that's what they assumed for us, the sampling distribution is normal. That means we don't worry about rule 4. The rule of thumb doesn't come into play. We're assuming automatically that's normally distributed, and so is this for any sample size whatsoever. Certainly n equals 16 would work. So we'll use that assumption when we go through the problem. In section 12.2, we will be using that rule of thumb coming up. I think that's the reading of the whole problem and all the information we could pull out of it. Any questions or comments so far, folks? Okay, first thing it wants is, oh geez, I keep letting these sneak through. The unknown parameter or population characteristic, if you prefer. This time, the thing that's unknown is not P. We have to write out this to start. It's a little bit tricky because we're used to seeing unknown population characteristic or unknown parameter. We usually wrote P because we were dealing with categorical data. So a lot of the work we're doing is really just trying to change our mode from categorical to now numeric and all the new things that come along with it. I'll try to point out all of these as we go through the notes. So for this one, we can write mu is either the population mean or the true population mean, anything along those lines. I'll go with, just to emphasize, it's a true and unknown value. Mu equals the true population mean of, and then dot, dot, dot. Pretty much for part A, if you have numerical data, the problem is going to start off like this when you describe your unknown population characteristic. We have to say, or excuse me, we have to use the symbol here because we're not using P any longer. And we have to say this as opposed to proportion. So we're not saying proportion any longer. Either say mean or average is a great word there as well. Let me put here, mean or average. Average is not too bad because if you just talk to a person who hasn't taken statistics, they're going to know what you're talking about more often if you say average as opposed to mean. At least that's how I perceive it. But it's truly optional which language you want to use here. But now we have to use the context. And the context is what's going to fill out the dot, dot, dot. Any volunteers for what should go next? There is a trick to this that actually wasn't a trick we could use when we had categorical data. The trick, now that you have numerical data, is take a look at these numbers. If you averaged all those numbers, you're estimating mu. Now, we're not trying to put a number down on mu, but if you look at those numbers again, it tells us the context. Let's backtrack. It says, here are the findings in becquerels per kilogram of dry tissue. So we're taking the mean of becquerels per kilogram. Let's move backwards. Becquerels per kilogram of what? It was of all Pacific bluefin tuna. So that's what we're trying to describe right here. The mean of the entire population of Pacific bluefin tuna after that meltdown. So let's say true population mean of radioactive cesium tissue concentration for, I like using this word here, all, If you left it off, it's not a big deal because we did say population mean, so it's almost redundant, but it's good to emphasize, at least in our own minds by writing this, we're talking about all Pacific bluefin tuna. So all, let's just say Pacific bluefin tuna. And at this stage, it becomes a kind of a judgment called how much we want to put in. If you left it right here, part of me might say, well, that's vague. There's different populations of Pacific bluefin tuna. There was the population before the meltdown, which was very different than the population 4 months after the meltdown. But if it feels like you're copying in like more than 2/3 of the entire problem, you might have could leave possibly some of that just to the problem itself or context. I'll say here, just to finish it off, all Pacific bluefin tuna, 4 months after the meltdown. And if you say the meltdown, I think most people are going to assume you're talking about the most recent one in 2011, the Fukushima Daiichi reactor that melted down. So you can leave some of the original problem to carry that context. Just bring in enough so you feel like you're capturing the heart of what the problem is all about. Any questions about that so far? Okay, the things I left off were they were caught off the coast of California, those kinds of smaller details. But we brought in the main context, so I think we're in pretty good shape right here. Now, next question asks us, what is the mean of the sampling distribution of X bar? Now, at this stage, we're just using the central limit theorem. This is rule 1. And for rule 1, it gives us the mean written in this way. It's the mean of the sampling distribution of X bar, so we write it this way. Mu sub X bar. And that's just equal to mu. Unsatisfying in a way because we don't have a number of this for this value mu. This is the unknown parameter that we're trying to estimate. But that's all they're meaning for in this problem. Just say what it is, we'll put in mu, and now we know what mu represents as well. Next, it wants the standard deviation of the sampling distribution of X bar, but go back up to that central limit theorem above, and this is rule 2. The reason I knew it's rule 2 is because they asked for standard deviation, and they also mentioned of the sampling distribution of X bar. It takes a lot of oxygen just to say that, and so that's why we like this symbol. Standard deviation of the sampling distribution of X bar is sigma X bar. Way easier to say if you're using symbols. But this one is also a formula. Not as simplistic as this one. It's a formula that we write in as sigma that we divide by the square root of the sample size n. So for rule 2, we can calculate this value because somehow, some way, magically, we do have sigma. It's 2.95 in this problem. I just want to emphasize again, that's pretty rare to have a known, assumed true value of a sigma in a population when mu itself is unknown. But if they gave it to us, we can work with it. So let's plug that in. From above, look up the value of sigma at 2.95. And notice we had to know that they're talking about sigma through this statement here. The buzzword is they said population standard deviation. That's how we know it's sigma. It's going to be a 2.95 going up here. We're dividing that result by the square root of sample size, which we identified to be 16. And now it's just a calculator problem. Let me try this side-by-side thing out. This is kind of exciting. For the first time, we can have a calculator side-by-side with an actual window. They're spoiling us. So let's go and hit. Not sure what we were doing over here, but this was last week when we were working. So we just are going to type in 2.95, hit divide, and we will need to go second, and this button here to get the square root out. Sample size of 16 goes in, and that's it. That's our standard deviation. This one we're rounding to 4 decimal places as a 0.7375. Actually, it looks like that's not rounding. It's exactly 0.7375. And so we did it, folks. That's our rule 2 for the central limit theorem. Any questions so far? Okay, next. This one I think is a little bit tricky. They're asking us to sketch a picture of the approximate sampling distribution of X bar. But if you think back, go back down memory lane, here's what we're really doing in this problem. The instructions aren't formatted the same as when we did this in section 9.3, I believe. No, excuse me, 8.3. Because the wording in the web assign was very specific. Here they changed the wording, but what we calculated was the center. What we calculated here is the variability. And when they say sketch a picture, we're now just sketching the shape of the approximate sampling distribution of X bar. Now, the way we're going to do this one is through rule 3. The reason we know we can use rule 3 is they said right here in yellow that the measurements follow a normal distribution. In other words, these 16 observations came somehow, some way from a distribution that's not approximately normal. We're claiming exactly normal. It's a bit of a lie, but we're going to run with it. And so rule 3 says sampling distribution of X bar is also normal. And so its shape would look like this. We're back to section 6.5 if we're calculating using this model, because now we have a normal distribution. It'll be mound shaped. It's going to peak right at mu. But sadly, mu is unknown, so we don't know where that peak is. So mu of X bar is equal to, let me make that penmanship work a little bit better. Mu of X bar is just mu. The other thing that we can specify is that sigma of X bar, we found a value for that at 0.7375. So for sketching a picture, this is really all we're going for. A web assign is like multiple choice. They'll give you models like these. Some of them are going to be skewed. Some of them will be completely flat, but some of them might look just like a perfect normal distribution like this. That's the model you want through rule 3 of the central limit theorem. Well, any questions at all, folks, to this stage? Okay, now this is the fun part. We're going to use the empirical rule to approximate a 95% confidence interval for mu at round to 2 decimal places. So finally, we're calculating the confidence interval. And this is the portion where we're doing this about how they would have done it historically. So the formula we will use only in 12.1, we're going to make a slight modification to make it a better formula, is this one. It's going to be X bar plus or minus. I want to put this next portion in red, Z star. Historically in the past, and again, this is not too long ago, this is within 100 years, people were using Z star right here. Then we didn't use a standard error in the past. Instead, we used sigma over root of n. And if they didn't have the value for sigma, instead of sigma, they would have used S, the sample standard deviation, right exactly there on the red dot. That was a bit of a problem. The results were okay, but folks noticed with small sample sizes, something was a little bit amiss. Our sample size at 16 is not too bad. By small sample sizes, I'm talking sample sizes around 3, 4, 5. That problem with this was starting to become more and more apparent. But still, this is a fun problem to do. It's a good review problem in a certain way. And this is about the format of the confidence interval if we were in section, say, 10.5 or something. That was section 9.3 is where we did that confidence interval. Sorry, it must have been a long break. I'm forgetting my section numbers. So if we're going to calculate this thing, probably the first thing we should go for is X bar. The problem never actually supplied the sample mean X bar whatsoever. So let's go up here. We need to import this data and find our summary statistics. This is definitely something we'll have to do on the final exam, so you can consider this pretty much a review problem at this moment. The reminder is, if you need to calculate statistics, you need to import the data. So we need to go to the stat key. Once you click on the stat key, immediately hit enter to begin importing data. Looks like this is all blank. And so let's put them in one at a time. I'll go row-wise. If you notice I'm putting in a typo, feel free to just call it out. That's never considered rude. Oh, and there's one. Okay, so it says 16 right here. That means we're on the last one for the sample size of 16 at 15.6. So it looks like we've got all the data in. Anyone recall the next button you have to hit if we want X bar and S? It's definitely been a little bit of a while. Exactly, hit stat key again. It pulls up the menu here at the top, and we want to go to calculate. Then once you go to calculate, everything is pretty much set up. Just keep on hitting enter. Double check, it says L1 here, but we've never had a reason to change that, so it should stay as L1. If you loan your calculator to siblings or anything like that, double check this stuff for sure. Then finally, this is what your output's going to look like. So we have a sample mean up here, and let's take a look at this. It says SX, that's the sample standard deviation. It was 2.80092. Let's record both just so we say we did it. We have X bar equals 10.3125. It says to round to 2 decimal places, but this is an intermediate computation. We want to keep as much precision as we can until we get to the end answer. Then the next value, S, the sample standard deviation, is 2.8009. I'll keep that one to 4 decimal places. And we don't necessarily have to use it because we know sigma in this problem. But let me highlight this and this. Let me just fix my color coding as well. Historically in the past, and this is recent historically, when people calculated the confidence interval for X bar, where you see that 2.95, they didn't do that. They knew that that's a sketchy thing to do. If you don't know mu, you probably don't know sigma. So instead, we put in the estimate 2.8009 right up there. If we do that here, our answer is going to be just a little bit more accurate. So let's make that estimate happen right here as well. So we're going to plug in a different value in this location. It will no longer be the true standard deviation of the sampling distribution of X bar, but our confidence interval is probably going to be more accurate because we're using the real data in our confidence interval right here, not a supposed value that was given earlier on. There is one small problem with that. If we use an estimate for that statistic right there, well, we have opened a brand new can of worms. We don't know how accurate that estimate is. We haven't specified the error in it. There's no confidence interval for it that we want to give. And so the correction is going to be at Z star right here. Let's make a note of it in preparation of the next section. In 12.2, we use T star instead of Z star. So when we put in sample data right here in for sigma, like we're about to do, that value here gets bigger. And it gets bigger in a very methodical way. So that's what 12.1 is going to specify, or excuse me, 12.2. But we're not there yet, so we're going to proceed and do this problem like it was done historically in the past. Any questions first, folks, before we start plugging in the information? Okay, well, let's go down the line. First thing is X bar. We calculate that to be 10.3125. We're going to now add and subtract a critical number Z star. And the way we find it is exactly the same as how we did it for P hat, but that will change in section 12.2. But just as a review, let's go look it up. At 95% confidence, it ought to be 1.9600. But just for emphasis, let me show you where you ought to look. Go to section 9.3. And this table still continues to be very valuable. Not as much in chapter 12. We're only going to use it once in chapter 12. But in the final exam, I would definitely want this for anything related to P hat. At 95% confidence, we'll use 1.96. And that's going to multiply the value for S in place of sigma. We're making an estimate already right in this location. So 2.8009 goes right here and V with sigma. And then down below, it'll be the square root of 16, or just 4 if you prefer. So that's our entire method. I have a lot of stuff right here that would be going to the calculator, but if you're comfortable with it, it's really not too bad. We're going to do like before, estimate, and the thing in the middle, recall it's not P this time, it's mu, the mean value or the average value of all the Pacific bluefin tuna 4 months after their meltdown. When we use a minus, we're doing the lower bound, so let's start plugging that in. It'll be a 10.3125 minus 1.96. I'll put it in parenthesis and just type this in verbatim, 2.8009. Then for the division bar here, click on divide. For the root, hit second and the power 2 button, left of your comma. 16 goes in there, and then parenthesis should be right here. You'll have to use your right arrow to get out of the root to put the parenthesis in the right spot. So there's our lower bound, 8.94. Now we are rounding to 2 decimal places, 8.94 becquerels per kilogram. Then repeat. By repeat, either use the up arrow or click on second and the enter button. Duplicates what we already put in, and we're changing one sign. Oh, I went too far. Right there, change that to plus. And notice how similar this feels. It almost feels like we're still in chapter 9.3, calculating an old confidence interval method. Now this 1 to 2 decimal places will be 11.68. Becquerels per kilogram of dry tissue, dry fish tissue, as gnarly as that sounds. So we've got it, folks. That's our entire confidence interval. And looks like I didn't ask for a practical interpretation, but that should have been the next step. Let's do that in right next. First, any questions at all, folks, on doing this procedure here? Okay, this is the real way we'll do the procedure in 12.2, with the only correction or modification, the thing you see in orange. We need a new value in place of Z star, and we need an explanation of why we have to change that value. But let's go back up and refresh ourselves of what mu even was. And then we just need a really fast practical interpretation. It goes pretty much the same way. This is almost verbatim the same kind of method as before. We double check the confidence because we want to mention that first just to not forget. So it was at 95. So now we can say we are 95% confident that, now we just have to say what mu is. It's specified down below, so let's read it out. That the true, I'll go with the true average of cesium tissue concentration for all tuna. I'm leaving off Pacific on this, but I'd say that's okay at this stage. Let's say for all tuna, 4 months after the meltdown. In my opinion, that time component is probably one of the more important things there to mention. So just 4 months after the meltdown, the average cesium tissue concentration we can say is between 8.94 and 11.68 becquerels per kilogram of dry tissue. I'll just write it out that way, becquerels per kilogram. So that's it, folks. That's our confidence interval procedure. And the only thing that's gone a little bit awry is where it said 95% confidence. It's not quite at 95% because in this yellow, we estimated sigma using sample data, which means there's a little bit more inaccuracy here. The interval should be slightly wider, and that's what's going to happen. T star is just a little bit bigger than 1.96. And the reason we have a new critical number is the moment you estimate a parameter here, with a statistic like S, we've actually left the normal distribution. People didn't notice this until they started working with samples that were very, very small. We're looking at next the student T distribution. Student is, what was that? It's a pen name. This was published anonymously, and it was actually a form of, we'd probably call it corporate espionage at this point. Gossett worked for the Guinness Brewing Company, and he was working with sample sizes of 4. He noticed this whole method is not accurate like you'd expect. Something was wrong in the math. He actually worked it out, developed a brand new distribution called the T distribution. That's where T star comes from. And Guinness told him, you cannot publish that. That is a trade secret. We are going to rock the beer world with our new scientific methods with this distribution. Gossett decided that just wasn't fair. Mankind needed to know this procedure. So he published it under the student T name. So because of him, well, we probably would have found it out, but because of him, we found it out when we did. We were able to enter a new age of statistics, go from Z star to T star, and now all our methods became more accurate instantly once that became published and widely read and adopted. So Gossett is definitely a role model for modern times. Not saying commit corporate espionage, but you feel like there's some information that's under wraps, you ought to let it free. The NSA probably disagrees, but that's what we're going for next. Any questions at all, folks, about what we've done here or what we're about to do? Yeah.
I guess why we're using the two separate. I mean, I know they're like similar in value, but standard deviations, like for part C and part D, like values, that's like, oh, I don't know, like I'm not like that.
Well, kind of major why is we're trying to go towards this section right here, confidence interval for a population mean. And we're going to discover that there's a big problem with this. We don't never normally know sigma. That problem was an exception, and it's still even questionable if they really knew sigma. What we're actually going to do is calculate a standard error. That standard error is going to be S over root N, which is what we did just right now. We typically put S in, just like we put the value for S right exactly here. So that was the major reason I did it right here. But we have to then make a correction and start using T star for our new critical value. But does that answer your question there?
I guess I just think it's like when I see the sample distribution of X bar, that it would be like from the same pool that we're, like, I don't know, it would be like from the pool of values that they're giving us that we find it from when we make the confidence interval. So I guess that's probably, I think I'm just like,
Gotcha. Yeah, we could have done this entire procedure and just used the value of sigma. But the only reason, again, that I used the statistic was that's how we're going to be calculating very, very soon. And yeah, that's really confusing where we just calculate this value, but then we never even used it. The major reason I put that there is it's also a WebAssign problem. You're gonna see that kind of question come up a lot. And so you'll have to calculate this just because it's baked into the problem. But when we actually go to use confidence intervals, we're not going to be using sigma. We're going to be using S instead. From the values of the actual data, yes. Does that help a little bit?
Yeah.
Yeah, I definitely agree with the confusion on there as well. Sorry about that. It is jarring to go from here, have the procedure written out this way, but do it actually slightly a little bit different. We're only ever going to do that once. Then when we get to 12.2, this is the only new thing we need to take a look at. And it won't be too bad of a computation. So one new thing, and we'll be ready for a whole brand new actual confidence interval. Other questions so far? Okay, well, thanks for asking that question there. That's a very good question to ask after going through all this work. When we come back next class, we're going to pick up right in section 12.2. Well, have a great night, folks. And it looks like the projector did not actually go out at all. We'll probably be here for the rest of the semester. No random problems, I hope.